just going to look at some trig integrals, and you'll notice I've labelled it trig integrals 1. That's because in extension 2 we'll also look at trig integrals, but in a lot more detail. So trig integrals, the basics, some of them are very basic of course. We know that we integrate sine, we get negative cos. We know when we integrate cos, we get sine. And sec squared is tan. They're the three very basic ones. But other ones that we should just see and recognise. Integral of tan. Tan you can rewrite as sine on cos, so we get minus the log of cos. Now I don't expect you to write it as sine on cos, I would be expecting you to see tan and go straight to minus the log of cos. Or, of course, you could go log of sec. This one here, I don't know that we've really talked about this one. But it does come up a bit. It used to come up a real lot when we did a topic called conics. It was in the old course. But the integral of sec tan is sec. So I throw that one in there as a basic integral that if you see it, that's what it is. Sec tan goes to sec. Complementary ratios. An interesting thing happens. If you integrate a complementary trig ratio, the answer will be minus the complement of the answer. Cos x, we know, gives us sine x. If we integrate sine x, that's the complement of cos, it should go to minus the complement of the answer. Well, the answer is sine, the complement of the answer is cosine, and we get negative cos. So that's the idea. So cosec squared, we know sec squared goes to tan, so cosec squared should go to minus cotan, so minus the complement of the answer. So cot x, well if tan goes to minus the log of cos x, then cotan should go to log of sine x. And I just mentioned about the sec tan, well cosec cot then should go to minus cosec. So what we're saying is, there's tan, well I'm now calling it the log of sec. So cotan, right, cotan is the complement of tan, so the answer will be minus, and then the complement of sec is cosec, so we get minus the log of cosec. So once you know one trig ratio, you can always get its complementary one as well. Squares of trig functions. So we've seen these ones recently. Sine squared, we can use our double angle result, change it to a half of 1 minus cos 2x. It then goes to x on 2 minus a quarter sine 2x. And cos squared, similar, but it's 1 plus cos 2x. So it goes to x on 2 plus a quarter sine 2x. And I suppose if you wanted to, you could change your sine 2x to 2 sine x cos x. And then so it becomes a half sine x cos x. If you wanted to. So sec squared, well that's an easy square one because we know sec squared goes to tan. Cosec squared, therefore goes to minus cotan. Tan squared, if we square tan, well, what I can do with this one is I use a trig identity. Tan squared is sec squared minus 1. So integrate sec squared, we get tan x, integrate the minus 1, we get negative x. Therefore, if I want to integrate cot squared minus cot x minus x. Notice the minus was only on the trig part, the thing that involved trig. It's still minus x on that. So be careful with that. So we get minus the cot minus x. So let's do some. Cos squared 3x. I'll use my double angle result. That becomes a half of 1 plus cos 6x. And we end up with x on 2 plus a 12th sine 6x. Ooh, sine x cos 2x. Products to sums. A half sine cos must have come from the sine expansion. So it'll be sine a plus b, x plus 2x, 3x, plus sine a minus b, x minus 2x is minus x. But of course sine is an odd function. So that becomes sine 3x minus sine x. And now we integrate both of those. So that's using our product to sum idea. Sine x cos cubed. Well, hang on a sec. I know the derivative of cos is minus sine. So I'm going to create the derivative. It's now in the form of derivative times some function to a power. So I can just add 1 to the power over the power. Cos to the power of 4 over 4. And you'll notice my minus has disappeared. But if you look closely, the other thing I've done, I swapped the limits around. So remember, you can always swap the limits around if you want to get rid of the negative sign. Again, you don't have to, but Subbing in, we get our answer 3/16. So just some trig integrals to play around with.